So this is the 25th lecture of this course, and today I'll start with the first unit, unit 1. I am done with your 5th unit with Boolean algebra and logic gates. So this is your first unit of a syllabus, and the topic mainly we will discuss in this particular unit is about the semiconductors. Semiconductors. Now electrically, solids are divided into three categories, if I say. That is conductor, semiconductor, and insulator. And this classification is done on the basis of the conductivity or on the basis of a diagram that is called the energy band diagram. Energy band diagram. So before exactly coming to these semiconductors, first how the solids are divided into conductor, semiconductor and insulator on the basis of this energy band diagram. And what is this energy band diagram? I'll start with this first. So I'll start with the topic that is called this energy band diagram. What do you mean by the energy band diagram? Now, before I come to this energy band diagram, you must have done about an atom, and or I say that an isolated atom. Isolated atom. Now, an atom, that an atom has a nucleus. An atom, it has a nucleus. A nucleus is there. And suppose I say this is a nucleus which has neutron and proton. And then you have certain orbits here. And these orbits contains some electrons are revolving around these orbits. You have some electrons here. Suppose you have another one. You have this nucleus here. A nucleus which contains neutrons and protons, of course. This will have neutron as well as proton. And these are the electrons. Of course, this will have certain shells. Now, it has some electrons. And of course, this electron number is given by 2n square, this model, where n is the orbit number. In first orbit 2, then in second will have 8, then 18 and so on. So there are certain electrons here. So suppose these are the two atoms of same material. Same. Suppose I say that there is also sodium and there is also for sodium. Of course it will have 11, 2, 8 and 1, but I am showing only this much. Now the point is that the energy, as far as the energy of an electron in an isolated atom, depends upon the orbit number, or I can say that the energy of electron depends upon the orbit, that in which orbit or in which shell it lies. And it is something like this, that you have suppose I say that this is the energy. Here it is showing the energy. The energies will be something like that this, for suppose I say this is the energy level for n is equal to 1. This is the energy level for n is equal to 2. This is the energy for n is equal to 3, and so on. Different. Of course, this is given by Bohr's model. Bohr's model. But this is for an isolated atom. Now what happens? When I talk about a crystal, let's talk about a crystal. Atom cannot stay isolated in nature. So how a crystal is formed? For example, suppose I say for any material, suppose it is any element, so it is sodium only. A sodium crystal, suppose this is a sodium crystal. This sodium crystal is formed by various atoms of such type when they come closer. These atoms, these are various atoms here, and a sodium crystal is formed. Now suppose I say that this is a sodium, or any atom or any particular material. I say this is the nucleus and it will have some electron. This will have an electron. Let's take only one, or let's take another one. There's a nucleus here and it has some electron here. Now what happens that they come closer. These atoms, they come closer in order to form a crystal here. Now what happens that when they come closer, what will happen accordingly? Say this is the first atom, suppose I say. It's a nucleus here. I'm showing only one orbit. This is neutron and proton. And of course there's an electron here. And there's another one. And suppose a covalent bond is formed. You know what is a covalent bond? This is the nucleus of. This is the second one. Suppose I say that this is the electron of this particular atom. And another one, I say that this is the electron of this one. These are representing electron. Now what will happen? The point is that, of course, suppose it has some other electrons also. This also having some other electrons also. Now what will happen? That look at this particular, this blue one. This blue one is, suppose I say nucleus N1 and this is N2. This blue electron is the electron of this particular atom, and this green one is the electron of this particular atom. Say these are the two ones. Initially I say that suppose this was in shell number 1. Both of them were having the same energy. Either this or this. In an isolated case, this will have the same amount of energy, whatever it is. Now, when a crystal is formed, this will have this atom. Initially, this particular electron was having a force of attraction due to only this particular nucleus here, or the protons available in this nucleus. Similarly, this one was having the force of attraction due to this interaction because of this only. But when they come closer, or when a crystal is formed, what will happen? That this particular electron of this atom will have interaction not only because of this, it will have an interaction because of this nucleus, it will have an interaction because of this nucleus, as well as this will have an interaction because of this neighboring atom. This electron, this particular electron, for this, when it comes close to this, when this particular electron, it comes close to this, it will have an interaction, a kind of interaction, a type of interaction, of course with its own nucleus, with this electron, and with the neighboring electron, I can say, and with the nucleus of the neighboring atom. So naturally the energy will change. Similarly, there are various atoms are there. So it is no more energy. We say that this is a energy band is there. So for a crystal, I can say you will have new interactions. For a crystal, the electrons of a crystal will have new interactions, and those new interactions are due to, I can say, are because of, first of all, first thing is the electron of neighboring atom. Electron of neighboring atom, and secondly, this interaction will be because of the nucleus of neighboring atom. Nucleus of neighboring atom. When this come close to this electron will have interaction because of this neighboring electron, as well as it will have interaction because of this neighboring nucleus. Of course, it will have interaction with its own nucleus also. That is a different thing. The point is that because of this only, some energy will change. Of course, energy will change, and not only for one atom. There are various atoms of such nature. A crystal is formed by various atoms. So in spite of having this discrete energy level, you will have a, now I can say, suppose this is the energy E. This particular outermost shell, I can say, it will have a different kind of different energy. All the electrons will have different energies, and in spite of calling it as an energy level, we call this as an energy band. Energy band. Remember that. See, suppose this is suppose I say that there is a crystal here. Let's take it a crystal here. Alright, and this crystal is formed by various atoms. Suppose this is formed by various atoms here. One atom is this, another 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 is this. These are various atoms, and they all have a nucleus. I am showing this nucleus by a dot. This nucleus. Now suppose I say that you have, this is the first orbit only, and electron is here in this first orbit, and here this electron in the first orbit. Even in the same orbit, even of the same orbit, the different electrons, although they belong to the same orbit, may have different energy. So suppose I say that there is the energy of the first or the nth band. So nth band, this electron will have different energy, this electron will have different energy, this electron will have different energy, all belong to the nth band, and we say that there is a band of energy. There is a range of energy, we call it there is a band of energy. That is what I mean to say, that each electron will have different energy even if they belong to same orbit, or we say that same subshell. So I am writing one more point here, that each electron will have different energy. I can say will have different energy even if they belong to, even if they or it belong, it means electron, it belong to same subshell, same orbit or same subshell of isolated atom. So the point is that when a crystal is formed, in spite of having these discrete energy bands, discrete energy levels, here the electron of first orbit will have this only, second electron will have this much energy, third electron, every electron of third orbit will have same energy till this atom is isolated. But once it becomes a crystal, first orbit, same electron the first orbit, this electron of first orbit and this electron of first orbit will have different energy, because it has different kind of interactions. So this is about your I can say how a crystal and difference between the crystal and isolated atom, the difference between this discrete energy band and this discrete energy level and this discrete energy this energy band here. So suppose let's take an example of say let's take a semiconductor only. Suppose I say that consider a silicon atom. Suppose I say consider a silicon crystal with n silicon atoms. Suppose I say, I mean to say that you have the silicon crystal here. A silicon crystal is here which is formed by n number of silicon atoms. These are silicon atoms, and n number of atoms, they form a silicon crystal. Remember that this n is not a small number, it is of the order of 10 to the power 23 and 24. So suppose it is like this. Now let's consider the atomic structure. You know that the atomic number of this silicon is 14. And if I write the electronic configuration, it is 2, 8, 8 and 2, 10, and 4, 14. Or I can write this as 1s2, 2 electrons the first, 2s2, 2p6, and 3s2, and 3p2. Door charge 10, yes, 14. So this is the electronic configuration, and if you look at this, we are mainly interested in this outer energy level. This is the outer one. This is the outer energy level. We are mainly interested in this outer one. The most affected are the outer electrons only, or the outer, we will discuss the outer energy level only. That is the outermost shell of an atom, or accordingly of a crystal also. So this is your outer energy level. Now how many electrons are there? If you see, there are 4 electrons in the outermost shell. So since the number of atoms are n, so okay, let's take that for first one. Suppose I say that how many electrons are there in the first one. Let's take it this way, that number of electrons, I say number of electrons in outer orbit, in outer orbit or outer shell of each silicon atom is 4. In the outermost shell, how many electrons are there? There are 4. So number of electrons in the outer orbit of each silicon atom is 4. Now there are n number of silicon atoms, therefore I can say that the number of electrons in the outer orbit of each silicon crystal, no more atom but it's a crystal, it will be 4n. In one there are 4, so n number of atoms are there, it will be 4n number of electrons are there. Now in outer energy levels, if you see, these are the energy levels. If you see that these are the energy levels, so total energy levels are 8, although 4 are filled. Or I can say that the number of outer energy levels, outer energy levels available in each silicon atom. How many? 8. Naturally 8 are there. Like I say, it is 2s and 6p. Although 4 are filled, it has 6. Outer will have 6 one, 8. So 6p. Out of which I can say that the number of this much, it is 6p. So number of outer energy levels in each silicon crystal, in crystal it will be 8n, that is 2ns plus 6np. This I can say it is 2ns and 6np. This much. I hope this is clear to you. Now out of 8 energy levels, 8n energy, total energy levels are 8n. So I can say that out of 8n energy levels, 8n energy levels, how many are filled? 4 are filled. We can say 4n are filled. There are 8n energy levels. In one there are 8, in n atoms there are 8n, and out of them 4 are filled, or I can say that 4n are filled with electrons, and at the same times that we can say that 4n are vacant, of course at 0 Kelvin. Now 4n are filled and 4n are vacant. The point is that now on the basis of this I'll make an energy band diagram. On the basis of this only I'll make the energy band diagram. And now what happens, just see, some are 4n are filled and 4n are vacant. Now I'll draw the energy band diagram of this. What will happen, just see. If I make the energy band diagram, let's use a different color. If I make the energy band diagram, on one side I take this energy. Just see. Suppose I say that I take this as 1 upon r, where r is the inter-atomic distance. This r is inter-atomic distance. What I mean to say, that you have one atom is this and another atom is this. This distance is r. Now when it comes close to this, of course when r will decrease, 1 upon r will automatically increase. Once it comes here, then a crystal is formed. Till this distance is more than a sufficient level or a threshold level, it is an isolated atom. So in order to that this is not isolated, it becomes a crystal by coming closer. So it means here I say that r is decreasing, 1 upon r is increasing this in this direction. It means that in this direction r is decreasing. It is, I hope that this point is clear to you. I assume that R is decreasing in this particular, increasing in this direction. Now let's take the two levels of this. Suppose initially I'll not, the one level is this, and one level is this. Suppose I take it this way, or let's treat it this way. Now what will happen initially, this is, you have two levels. Outermost level is this level, 3s level and 3p level. I am interested in 3s and 3p. Now in 3s you have 2 electrons, and in 3p you have 2 electrons here. So till suppose I say that this is the level, this is the point where it is isolated one, it is isolated, and now they come closer. Now when they come closer, this is the energy. This energy state will no more be, I'll show it here. Forget this line is not there. Now what will happen after this? This, in spite of this discrete level, now you will have energy levels. Now what will happen? This energy will increase or decrease accordingly. Either the energy, this will have some increase in energy, and this will have some decrease in energy here. It will be something like this. And if you see, it becomes this way, and this goes like this. Similarly, it comes in this direction and it goes like this. The point is that this, in spite of this discrete energy level, this is the discrete energy level, when they come closer, it becomes a crystal. It becomes a crystal. The electrons will increase, will have, some electrons will have increase in energy, some will have decrease in energy. Similarly in this level also, some will have, this is of course this 3s and 3p. Initially both had 2n number of electrons. This also 2n, and this is also having 2n number of electrons. If you see, 2 in each, it has 2n, 2n. Now what will happen? Naturally these electrons, they will decrease, the energy of this electron will decrease, and they'll come to this level, this particular energy band, and this is called the filled energy band. It has been filled, and this becomes empty. This is empty. The 2n electrons already it had, and 2n from this side, this is filled. This is filled, and this band is called the valence band. This band is called the valence band, and this particular band is called the conduction band. The electrons in this level, they lose their energy and come this in this band. So this is a filled one, and this empty conduction band, and this gap between this and this gap is called the forbidden energy band. Forbidden energy band, and this diagram is called the energy band diagram. Now based on the gap, this forbidden gap, how much is this forbidden gap, the solids are divided into conductors, semiconductors and insulators. So I hope that this energy band diagram is clear to you. In the next lecture I'll come to exactly the classification of this conductors, semiconductors and insulator, and then I'll move to the topic semiconductors. So I'll stop it for the timing. Thanks.